Okay, so in this question they are talking about n, the set of natural numbers, and they have given four different sets PQRS, and they are talking about which of them are countable. Okay, so basically all of them are infinite sets, and infinite sets are of two types, you might be knowing: countable infinite set and uncountable infinite sets. And they're asking about which of them PQRS is countable, right? Is or are countable. So that thing we are going to decide among PQRS. Now what is countable? So countable, the basic and the most trivial definition is that anything which can be mapped one to one to the set of natural numbers, that thing is countable, right? So if somebody says you that okay, set of all even integers, that is countable infinity, right? Because k to 2k you can directly map. So in that sense, but if somebody says you from 0 to 1, the set of all numbers, irrational, irrational, everything, right? So even irrational only, that also. So that thing is uncountable. But why? Because there is no pattern through which one by one by one by one you will go through and enumerate everything. So you cannot map it corresponding to the set of natural numbers, right? So in that sense, this is uncountable infinity. Now among this they are asking about countable. Okay, so let's start with the first one, p. Set of rational numbers, p, positive and negative. Doesn't matter. What you can do is that you can have something like that. Okay, so let's list all the natural numbers, positive or negative, something like this: 0, 1, -1, 2, -2. Okay, so 3, -3, like that. You can list everything, right? Similarly, 1, -1, 2, -2, you can list, right? Now any rational number, you can write it in the format of p by q, where p and q are integers, right? Even if it is a negative one, so what, let's say it is -5 by 3, then you can write it like -5 by 3, or you can write it by 5 by -3. So in that case, one is going to be -5, another one is going to be 3, then that is a point over here. The point what I'm trying to make here is that every rational number can be enumerated here in this matrix. Understand? So if we try counting everything, then in that sense we will never ever go miss any particular rational number, because whatever rational numbers, I don't care what is p, what is q, somewhere in this matrix it will come. And if I count something like this, and let's say this, and then something like this, or whatever, if I start counting everything, then everything will match. There is no doubt about it, right? So in that sense, first one, second one, third one, fourth one, I can map it to set of natural numbers, right? One to one. Okay, because this is also infinitely going and n is also infinite, I can map it one to one the way I am sorry, counting it, right? In that sense, this is a rational number. You might have seen already this pattern of finding countable infinity if you want to enumerate it like that, right? So you might already be knowing that the set of rational numbers is countable, but I just showed you an example. Why? Because we figured out that definitely set of rational numbers is countable, but this figure was going to help us in identifying something more. So for example, let's say we are talking about q, which is a set of functions from 0, 1, let's say 0 and 1, two elements are there, to n. So n is what? N is again a set of natural numbers. So entire set n is there. So 0, 1, -1, 2, -2, everything is there, right? First of all, what is the number of total number of functions? They are talking about set of functions. So what are the what is the total number of functions that can be mapped in this fashion from this set to this set? That thing is n square. Why? Because this thing can be mapped in n ways, this thing can be mapped in n ways. So total number of ways is totally n into n, basically n square, right? Now the point is that if n square is there, then the same fashion in which we did last time, we can again do a sort of similar sort of mapping, something like, let's say 0, 1, -1, 2, -1, 2, -2, 1, -1, 2, -2, all numbers in this fashion are mapped. And then I will have a convention like, okay, so when I'm saying that 0 is mapped to, let's say 2, and 1 is mapped to, let's say, -1. So this is what? This is one instance of a function. Out of all the functions and square functions, this is one instance of function, and each such instance is basically a tuple. So you can say that, okay, 0 is mapped to 2, 2, and 1 is mapped to -1. So 2 comma -1, this tuple, and this tuple you can this is basically what? A coordinate, right? X comma y coordinate. In that fashion you can understand. So if you can say that let's say 0 is mapping here and 1 is mapping here, this 2 comma -1, you can put a point here, right? That I'm talking about this thing. So in that sense you can understand that every function is an instance of every function can be mapped to a particular dot in this matrix. Understand? And in that fashion, if we want to enumerate all the functions, so we are talking about a set of functions, is that countable? That will boil down to, is that enumerable in that sense? So it is enumerable. Just say whatever happened in the last part about all the set of rational numbers, in the same fashion we can move here also, right? So in that fashion, I know that if I'll be moving and I'll be enumerating, going through all of them, then I can never miss a function, because every function will be a sort of a dot in this sort of n cross n matrix, right? So I will not miss anything. I will enumerate everything, and that makes it, that analysis of us definitely will make it countable. Okay, so we have figured out that P and Q both are countable. Okay, now R and S. Okay, so R is not countable. So basically I'll tell you that you can intuitively understand it. Like here they are talking about n201. Okay, so here they have reversed the situation. 0, 1 is there and this thing is n, all the elements. Now you can understand that here the total number of functions will be 2 raised to the power n. Okay, now earlier we were talking about n square. Now here talking about 2 raised to the power. Now this is exponential, and you understand that if n is increasing, the entire one dimension is increasing, right? So you cannot map that one to one like you could have done in even n square. Even for n cube you could do a one to one mapping, but you cannot do that for a situation where the dimension is increasing with respect to n, right? So there's no way you can do that sort of enumeration stuff, right? So this thing is not countable, right? Now let's come back to the last option, the set of finite subsets of n. Okay, so for that we are going to understand that, okay, when we are saying firstly, let's say set of all subsets of n, set of all subsets of n. Okay, what is that? That is definitely uncountable, because all subsets, you understand, this thing is going to be in this range, right? So if n is the size of a set, then what is the total number? All subsets means what? Power set, right? Again it will go in the range 2 raised to the power n. So that is definitely in the same pattern going to be uncountable. But my point is that this all are basically two types, right? All are two types, finite and infinite. Okay, so here they are just talking about the finite subsets of n. And what does finite subset of n mean? Finite subset of n means that, okay, those subsets of n which are of size 1, which are of size 2, which are of size 3. Okay, so there can be many such infinite subsets, right? But they're talking about finite subsets. So in that sense this thing is coming out to be countable. Why? Because there is a way, right? You can definitely know that, okay, one wala, I will first of all I am going to count all of them, right? 2, the size 2, whatever total number is going to be, I can count directly, like all of them. Similarly here also you know that, okay, total n elements are there, I have to choose 3 elements, right? And choose 3, only this many subsets of size 3 will be there, and I will count all of them, right? So there is a proper way you can enumerate all of them, and that strategy you can intuitively understand that that is going to make it countable. You cannot do that for infinite sets, but for finite sets you can make that strategy, right? So in that sense the set of finite subsets of n is basically countable. I give you an intuitive version of that. So P, Q and S. Okay, so P, Q and S, only these three, P, Q and S are countable, R is uncountable, right? So the answer is D.